Okay, hi everyone. I have two homework related announcements before we get started. So the first one is homework two is probably going to be released today. And by today, I mean today anywhere on Earth. So it will be out by hopefully the time you wake up tomorrow. And then number two is that we would love to have feedback on homework one. Like some people said it was taking a long time or like certain parts were difficult, and we'd like to make sure that we're trying to make the homeworks not easy, but like informative and helpful to learn about the things we talked about in class. And so we have a feedback form. We're trying to incorporate some game theory in how we're grading the feedback form, which is if 50% of the people in the class fill in the feedback form, everyone gets a free quiz. So it's an anonymous feedback form. And if everybody fills it in, you will get an extra 3 out of 3 on your quiz grade. So that will make it a little bit easier to get a good quiz grade. But that only happens if half the people in the class fill it out. So you can bug your friends to try to get them to fill it out. So, and the reason why we're doing this is we want to get anonymous feedback, but we want to get anonymous feedback, but we don't we want people to give us feedback. So this is our way to encourage people to give feedback while still being anonymous. Cool. Any questions? Okay. If not, I'll get started. We have two presentations today, I think. You're here. Who else was presenting? Okay, great. Um, Sounds good. So I would like to talk about agents, and I'm not going to talk much about training or designing agents in order to improve accuracy through architectural changes or language model changes, but rather focus mostly on the things that are related to doing inference in agents, because this is an inference class, but there's kind of like no way around some of the architecture stuff. So I'll be talking a bit about that as well. But basically, an agent is a system that iteratively uses tools to achieve a task. So it's not just a one-shot tool use, but it's using tools over and over again. Almost all agents nowadays are powered by large language models. There are possibly some agents that are not powered by large language models still. Anybody have an idea what those might be? What was an example of an agent that was that existed like 3 years ago or 5 years ago? Siri and Cortana are good examples, yeah, and they're maybe mostly not powered by large language models now. Any other ideas? What about the ones you use to get customer service when you call your favorite airline or something? Those are other ones that are basically based on trees, like if this and classifiers and stuff. And those, you still use, but now all the newly developed agents, mostly people are using LLMs. Um, Agents are interesting because they pose unique inference challenges in a number of ways. The first one is reasoning and planning. Um, and because of this, you have to do extra steps that require inference over them. Environment representation. So like how do you represent all of the output from the tool calls that you get? Long context modeling. So agents are probably one of the biggest long context use cases nowadays, in addition to things like summarization or question answering. Evaluation. I'm going to talk a little bit about this in case people want to, use agents and evaluate them. Another thing that we've been working on, kind of more from my personal experience is critic models. And critic models are models that are essentially similar to the reward models that we're going to talk about later, but I'd like to talk about them now because this is only agent class, and then you can remember them when we cover reward models later. And also multi-agent delegation. And I'm not really gonna cover this in that much detail, but I'll talk about it a little. Cool. So the first thing is some use cases for agents. Has anybody like built an agent to do something? Yeah.
They made one for simulate so users on a search engine. So they do a bunch of actions like predicting what will the user click and what's the next action the user is going to take.
Okay. Simulate users on a search engine. That sounds good. Any other interesting use cases? Okay, well, thank you for accidentally volunteering to talk about your agent. We have a bunch of different use cases. One of the biggest ones nowadays is software development, so code generation, debugging, and testing. There's kind of popular examples like Claude Code by Anthropic Codex, and also OpenHands, which is an open source agent that I'm developing that I'll talk about a little bit. Also web automation, so things like data extraction, form filling, testing, and things like this. And there's closed source things like OpenAI Agent Mode, if anybody has used this. And then there's open source ones that you can download and use in research, like browser use is a very popular example of this. Things for research and analysis. So kind of by default, a lot of the chatbot interfaces like ChatGPT or Claude now support things like information gathering and report generation. There's also things like Perplexity Pro. There's open source versions of things like this, like Open Deep Research, and there's like 7 different Open Deep Researches. So you can find one and pick your favorite one. And then there's also interactive environments like games, simulations, and robotics. So, things to play games like Minecraft and work on robots. So I have been actually building an open source agent called OpenHands is kind of it originally is an open source tool and then is part of a startup that I work with. And because of this, a lot of my best examples are from my experience with this. Basically, it's a software development agent that also supports web browsing and other varieties of tools. It's available here. I'd like to show a little example. So you can like click through and create a conversation. Anybody have something interesting I can do? I usually try to pick something that I want to do recently. Okay, here's one. Find the website for CMU Inference Algorithms class in fall 2025. Download the homework assignment and guess how long it will take to finish homework assignment 1. Okay, so let's see how accurate this is. Sorry. This is using GPT-5 and inference on GPT-5 is really slow. So I'm going to stop doing that and use Claude because I'd like it to finish before the class finishes. 4.5 came out. That's nice. Yeah, we just haven't updated the interface yet. So like GPT-5 has we run it with the like reasoning effort high, and the high reasoning effort takes a long time, but it's really good. So it doesn't make as many mistakes. But yeah.
You specify whether it's like a person or it's self-finishing or
That's a good point. If I ask it to guess how long software engineering tasks will take, it usually says like much longer than it actually takes. So it'll probably say like 2 to 3 weeks or something. But anyway, like because this is a demo, I'd like to just show you what it's doing. So here it's calling a search engine tool. It's calling a search engine tool to try to like find like search for this class. It found it taught by me and Amanda. And then it sees there's an assignments page. It's going to that and extracting the information from the page. And then it's cloning cloning the code to see where the code is. It's reading the PDF, so you can see that it opened the PDF and it's reading through the assignment and stuff like this. Scrolling down to read more of it to gather more information and stuff. I won't make you watch all of this. I'll like go back to this like to check on it when it's done because I don't want to spend too much time watching the agent work. It's kind of a failure mode of agents. You shouldn't watch your agent work. You should let it go do things and go back and check on it because it's too like fun to watch the agent do what it's doing. But that wastes a lot of your time. So cool. And any questions so far? Yeah.
What do you use, like LangGraph or LangChain or?
Yeah, so great question. LangGraph and LangChain are like tools to build agents. We actually decided not to use anything like this, and I can talk a little bit about the design decisions, but we have our own agent SDK that we designed specifically for this. And the reason why we did this is LangGraph and LangChain, basically my description of them and other things like AutoGen is they're kind of for fixed agent workflows. So it's like, I want to do this, and then I want to send the information to this and do that, and then send the information to this and then do that. And so they're particularly good when you have like a more fixed workflow. But in software engineering, or like the workflow is very various, right? Like I did I did something here that's like a workflow that I've never really done before. Like, look at homework and estimate the time. And so in order to make things kind of more diverse, we basically just wanted to create a single agent that could do lots of different things. So we didn't use that sort of scaffolding ourselves. So basically what you do is you add tools, the tools that you wanted to have available to it. And then the like framework that we created has all the like inference or all the methods that I basically will talk about in these slides implemented in it, but it's mostly not like doing delegation between multiple agents, which is what LangGraph and AutoGen are good at. Yeah. Cool. Okay, sounds good. Let's move. Actually, maybe it's done. 25 to 35 hours total. So we'll see if that is well, also we're going to have the feedback survey that hopefully everybody will fill out, so you can see how correct this estimation was. Cool. Let's go. So first, I'd like to talk about reasoning and planning. And the basic idea is that we talked about reasoning from the point of view of mathematical reasoning. And the mathematical reasoning, it's mostly kind of like deductive reasoning, where it's like, okay, I have this math problem. I want to apply my principles to perform, to solve the math problem. Here, it's a little bit different. It's like this is the information I have, and I want to combine it together to solve a problem in a kind of like fixed way. But rather, I would like to come up with the best idea of what to do next, given my overall objective. So this is more open-ended. The standard way of doing reasoning within language models is based on a paper called React, which is a framework where you basically do reasoning and then perform actions. And so this is in contrast to only acting. So you're given a task, and then you have an action, which is go to drawer one, and then the drawer is closed, open drawer one, you open the door, etc. But you actually add the thoughts here. And there's two reasons why you would want to do this. The first reason why you would want to do this is we've all seen that chain of thought like improves accuracy, and agents are no exception to that. The second reason is it actually gives you updates of like what it's doing in natural language. So you can see that it's saying here, I'll help you find the website. Great, I found the website. let's access it. I can see there's an assignments page. You can kind of like follow along what the agent is doing without looking at its actual actions here. So that's kind of like a major advantage of doing things like that. So accuracy and kind of legibility. So React is a method for basically multi-step agents that use reasoning. There's another method called CodeAct, and basically the idea of CodeAct is instead of calling individual tools with an agent, you have the agent write code that executes the actions for you. And the basic idea was like, let's say you wanted to you wanted to check the price of 10 different items and find the most expensive item or the least expensive item or something like that. The original way you would do this is you would make a bunch of individual tool calls. You would get the results of all of those tool calls, and then you might make another tool call or use the LLM to pick, the like highest price or lowest price item. But what you can do instead is you can just write a Python program that calls all the tools for you. And that was the basic idea behind the CodeAct framework. And what CodeAct does is it simplifies your action space because now all of your work is basically writing programs in a language like Python. And it also makes you be able to solve tasks a lot more efficiently. So this is pretty popular nowadays. And so now a lot of agents have kind of a like coding style action space where they can run Python programs or they can run Bash programs or other things like that. And this is important for inference, of course, because it's the difference between one action that generates a very large output versus many, many individual actions that generate a small and less complex output. So you could even like trade off between the two, right? You could have, even if you're using CodeAct, you can have an agent that prefers to write small chunks of code, and where it's more certain about the result, or write very large chunks of code where it's less certain about the result. So you need to think about trading off between those. Cool. Any questions about that? Okay. So another thing about planning with agents. So React is a very reactive way of doing planning. So kind of pun intended, kind of not. But like basically the idea is it plans in very small chunks, in that it is usually reasoning about the best next action to be performing. Another thing that we did in open hands and other libraries also, other libraries and methods have similar ideas, is we have a planning system that utilizes tools and that can set out a plan and then update that plan as you start executing the plan. So this is something that we introduced relatively recently, but it's been very useful and effective, is you have a task tracker tool. And this gives you structured task management where it basically will like come up with a task where you have different individual steps in that task, and then it can update the status every time. So it will like recall the tool every time a step in the plan it changes. So let me see if I can get it to do this. Check all of the classes and see if there are any missing references. Create a plan and check off each item of the plan. And I actually don't need to write the second sentence here. It'll usually do it spontaneously, but because this is a demo, I want to make like extra sure that it will actually call that tool. Let's see if that works. Yeah, so here it created a plan and it says like examine all starter code files, check the shared task example code, verify the requirements. And then it updated this to in progress. So now it's working on this part and it knows that this is in progress. So it will continue working on that. When it finishes, it will write done. And then when it writes done, it will make sure to include all of the other elements of the plan. And because of that, it kind of like refreshes the more recent context window to include all elements of the plan in the context window. And this lets it like not lose track of its plan. And this actually gets stored on the disk too. So it gets stored in like tasks.md. So like it can't just disappear from the context window. Another tool is a thinking tool. And the thinking tool basically gives the model permission to take another step to write a really long chain of thought. And so this was introduced by Claude when they introduced Claude Code. And the basic idea is like you tell the agent, if you need to think really carefully about something, write a like long explanation of what you need to do in this tool. And that tool has no effect whatsoever. It just like is there for thinking. And so it outputs this thought. And then in the next step, based on that thought, it can actually take the action. This probably technically isn't necessary if you have a reasoning model, but it's a way to turn a like moderately like maybe a shorter chain of thought model that wasn't explicitly trained for this into a model that can do this. So it's kind of like an inference time trick even because you're not changing the model, but you're giving it increased capacity to think. Cool. Any questions? Yeah.
Like the idea of React or any of the set planning, like you have a specialized reasoning model in the reasoning, this is very long and probably not consistent with what you are doing. In that case, like these frameworks don't really, they break down for those models.
So the question was, if you have like a reasoning model with a really long chain of thought, do these frameworks break down for the models? I think essentially everybody is doing React. There's like no agents without any reasoning whatsoever. So your choice is either to use a short chain of thought or a long chain of thought that was like explicitly trained for reasoning. And so in a way, the framework isn't breaking down. It's just like constantly present, I think. The extra thought tool, I think, honestly, may not be necessary if you do training. It's like a way to retrofit, extra thought into a model that was not initially trained for it. The task planning, I think, is still useful, probably, unless you trained a model to do that natively. But even if you trained a model to do that natively, it's not quite as effective as having like the plan stored on disk and, being able to recall it without it being in your context window. So it might not be necessary, but I think it still could be helpful. And it's at the very least, it's helpful for visualization to people who are watching your plans. So, yeah, great question though. Cool. So the next thing I'd like to talk about is environment representation. So like as we learned from the tools class the previous time, the tools have actions and they get observations. So then the question is, how do you represent these observations in your model? As I mentioned, I want to talk about inference related things, and this is important because these can be very large. And because they can be very large, this impacts how you do inference when you're working with agents. So the first type of environment representation, I'm going to maybe specifically talk about representing websites because I work with a lot of web agents, but I'll talk a little bit about representing code in files also. So the first type of environment representation for websites is text-based. And so what this does is this basically takes a website or maybe a PowerPoint presentation or some other thing that's not natively text and just converts it into Markdown. And so this is an example of what something like this would look like for the LTI homepage. And so instead of the beautiful LTI homepage that we've newly updated and everybody knows and loves, we get this Markdown representation, and it's very concise, very easy to use. I actually maybe didn't get this directly from the Tavily extract function, but We use a search engine called Tavily when we in OpenHands, but there's a whole bunch of other search engines that could be used for this that like kind of create these representations that are specifically for agents. One problem with representing it in text, though, is you can actually perform actions on websites, like clicking and scrolling and stuff like this. And it's not like in this markdown representation, we don't have a specific representation of the interactable elements on the site. So like, let's say I wanted to click on natural language processing, and there was a link here, there's no link. Or let's say I wanted to enter something in a text box or something like that. There's no text, no way to represent a text box natively in Markdown. So you'd either need to come up with a representation of Markdown, or you would need to do something like a text-based representation of the HTML DOM tree. And this is the standard way of doing this for web agents. It's called the accessibility tree, and it was originally created for screen readers for vision impaired people. So, you know, if you are not able to like actually see the site, you can put it into a screen reader and it will read the site for you. And so this is basically just reusing the method that was used there. And so this is what it looks like. And importantly, it gives you a ID for each of the elements. And if the element is clickable, you can then click on that element by selecting this ID, by calling a tool that basically clicks on this ID. So that's another thing you can do. So this is the original way that agents represented websites. Now it's becoming more and more common to represent websites through vision. And this is an example from a paper, Visual Web Arena. And the way it works is you take a screenshot of the website, and then around every element in this screenshot, you put a box, and then you put a number next to the box. So this is like the ID that I showed before, but this number, you can then like click on this number, and you also get a like kind of summarization of all of the elements with their numbers in text as well, just to like reinforce that these are the elements that you have access to. So this is called set of marks, and this paper applied set of marks to kind of vision-based web agents. This is actually, and sorry, one thing I should mention is when we're representing code, I think maybe I forgot to add the slide to this slide deck, but when we're representing code, another problem or files on your file system, you don't want to read a like 10 million line file by accident and completely destroy your context window. So another thing that people do is they either train models or explicitly give models tools that only select like a subset of the like lines of the file. And like there are file editing tools that allow you to do that. So that's about environment representation. Any questions here? Yeah.
In like visual environments, like I said, Mark's environment with this,
Mhm.
when you couple this image with text, won't the LLM or the VLM just end up paying a lot more attention to the textual data as opposed to the image?
Yeah, great question. Won't it pay more attention to the textual data than it will to the image? It depends on the LLM. One thing I will say is that LLMs are not natively good at understanding web pages. This was a major problem 9 months ago or 12 months ago, where certainly most of the open LMs could not understand web pages at all. And so, you know, they would not be able to do OCR, they would not be able to do character recognition, they would not be able to identify like which elements meant what. And so I think basically the good news is you can generate infinite sets of marks by essentially taking the web page and automatically writing the set of marks on it. And then you can say, okay, what is the 41st element on this web page? And then you'll train the model to be able to do this. And we actually have a paper called where we created a data set called multi-UI that explains like 10 different auxiliary training tasks that you can use to improve web page understanding. And so once you start doing that, the models start to be like very good at understanding web pages. And I think most of the kind of like foundation model companies are doing that sort of thing now.
Instead of marks, like caption marks are really close to each other, and the labels overlapping. What, like, doesn't that hurt more than it helps?
It does not hurt more than it helps. So people have tried doing this without set of marks, and doing it with set of marks is definitely more effective. So that's why people do it. But is this the optimal way of doing things? Maybe no. One other thing I should mention, actually, which is actually maybe I'll mention it in the next section. But yeah, that's a great question, and there's certainly more that could be done there, I think. Cool. I'd also like to talk about efficiency optimization. So like one really big challenge with agents is context length. So we have long conversation histories. In a typical evaluation of something like Swebench or Web Arena, which are some of the like benchmarks I'm going to talk about in a bit, I would say the conversation history can go up to as much as like 100 steps. For instance, so like 100 like maybe 50 tool calls, 100 actions and observations. This can be very long. This can get over hundreds of thousands of tokens. In practical usage, I have used agents for up to 2,000 steps. And so that's like tens of millions of tokens in your context length. And so most language models cannot handle this. Even if they can handle this, it becomes very expensive. It's particularly bad if you're doing something like web, because web pages can be very big. And so you need efficient context management strategies. Number one, which is really important, we're not going to talk about this until later in the class, but is prompt caching or KV caching. And basically the way this works is when you send a first output, when you send the first prompt, you can send the system prompt, the observation, and get an action. And then here you need to calculate the representations for all of them. But the next time you calculate the representations, you have the system prompt, the observation, and the action, and you've already calculated the autoregressive representations for these. And so then you just need to feed in the next observation and the action. And then the next time you have all of these pre-computed, and then you calculate the next observation and action. And so what this means is you can basically save all the compute that you use to calculate these, and that saves you a lot of money and time when you're running these. In reality, a lot of services will only cache the things that you had in your prompt. So some of them will only cache the system message and the observation, but in reality, you can also cache the action as well if you're clever about it. And we're going to talk about more details about this, so I'm not going to talk about all the details this time. Another thing I'll talk about a little bit is context condensation. And this is a way of taking in the previous context and removing some of it, basically summarizing it or removing it so that you can get better results. Within OpenHands, we have a number of different ways that we do this that are kind of representative ways that are used pretty broadly, including in other like coding CLIs like Gemini and Claude Code. But I'll just cover both of them here. So the first one is summarization. And so the way we do this is after we have done a certain number of steps, we take a portion of the previous steps and we feed it into an LLM and we summarize what happened in the previous steps. And what this allows us to do is this allows us to basically remove, half of the context while still keeping most of the relevant information. It's not perfect. Sometimes you lose information that would be useful later, but after a certain amount of prompt engineering, we have been able to, do this successfully. And you can see like our prompt within the code base if you're interested in the details about this. So from the kind of experimental results we did, we were able to see like 2x or even more cost reductions while maintaining performance on Sweetbench. We actually have a few kind of like war stories about this. So we did like experiments on Sweetbench, which is the very common benchmark that people use for evaluating coding agents. And then we like actually started using it. And it worked pretty well, but it did some really stupid things. So like, for example, it would send a pull request to like update code on GitHub. It would forget that it had sent a pull request. And then it would send another pull request over and over and over again. So we needed to modify the prompt to say, okay, remember if you've sent a pull request before and like other stuff like this. So it's not as simple, like it demonstrates the difficulty of like benchmarking in real use, but basically this overall idea works. Another thing that's really common in agents, this started out in the agents for Web Arena, which is the benchmark that I'm going to talk about in a bit, but is web context condensation. So web pages are large and noisy. There's actually two methods that I'd like to talk about. I only have one on the slide, but one method is after you have already processed the web page, after you've already sent it to the agent once, you can keep only the most recent accessibility tree or image. And so what that means is like after you've looked at it once, then you basically just remove it entirely from the history. So on the challenge here, I wrote prompt caching is less effective. You lose one of your inputs when you're doing prompt caching. Another problem with this though is like you still need to process the big web pages, and the big web pages can be pretty expensive. So there's another method in a paper called Mind to Web, which isn't in the references. Like most of these references are on the web page, but this particular one is not. And this is only a minor part of the paper, but they have an interesting inference time technique there, where basically what they do is they try to guess which parts of the web page are going to be useful first. And so what they do is they get this accessibility tree. They try to guess which elements in the accessibility tree are the most important ones to be looking at using a very lightweight, cheap model. And then they take all of those and all of the parents of those elements and feed only that into the language model. So that might also be a method that could be used to keep around more history while like not hurting performance. So I've not heard of a lot of people using it in this context, but it might be an interesting thing to try if you're interested in web agents. Cool. Any questions here? Yeah.
As well. Like for action environments like changes, and I suppose a lot of elements would change. Like and for example, the coffee example I have in my mind is for a search query, there are two search queries that are similar. The top 16 items shown would be very similar. So the environment representation you created at point A will be very similar to the next environment representation. So do you completely refresh the representation at every time, and what is the frequency at which this environment representation is updated?
Yeah, that's a good question. So like the question was, do the environment representations change? Like if you retrieve the same web page over and over again, do you like reprocess that web page every time? As far as I know, the answer is yes, you reprocess it every time. But I think there might be situations where you could save compute by not doing it every time, like especially like if you were running a really high volume search engine like Perplexity or ChatGPT or something like that, I could definitely think of wanting to pre-compute the representations for those web pages and getting them to work. So that seems like an interesting thing to try. Yeah. Cool. Any others? Okay. So the next thing I'd like to talk about is evaluation. There's many agentic evaluation benchmarks. I'll talk about a few specific ones first, and then I'll talk about a place where many benchmarks are kind of aggregated together. So the first benchmark that I personally pay a lot of attention to is SWE-bench, and I think a lot of other people pay attention to this as well. This is basically a benchmark for fixing issues on GitHub. So the input is a GitHub issue and a code base. And so it's like there's a data leak, this is the code base, and then the agent needs to generate modifications to the code base in order to fix the issue. And then the way this is evaluated is together with this issue, there were some unit tests that were introduced to check the correctness of the fix. And all of the unit tests that were introduced together with the issue must pass in order for you to get your full credit. And a select number of unit tests from the testing harness that existed before the PR also must pass. So basically, you need to fix the issue while not breaking things. So that's how it's evaluated. So there's 2,000 GitHub issues from 12 popular Python repositories. And because this is very popular, there have been a number of extensions. There's an extension called SWE-bench Verified, which is 500 issues that were specifically verified to be solvable based on the input to the issue. Based on the issue description. And the reason why is because a lot of issue descriptions are kind of vague, and you wouldn't necessarily be able to come up with the quote unquote correct answer from the vague issue description. And so SWE-bench Verified is an attempt to make all of them solvable. This is what everybody evaluates on nowadays, because it's just this, we don't really know what the upper bound on performance is, but on SWE-bench Verified, we think the upper bound is close to 100. So that's what people use. On the other hand, it takes a lot of the fun out of trying to resolve ambiguous issues and stuff like that. So, just because you get a good score on SWE-bench Verified doesn't mean you've solved all GitHub issues, which would require interacting with a human, to ask clarifying questions or something. But there's that. Another thing, this is all in Python. And so there's also things like multi-SWE-bench, which have different programming languages, and SWE-bench multimodal, which has multimodal data where you need to fix a front end and stuff like that. So a lot of different examples. Also SWE-rebench, which is updated every month with new issues. So a lot of examples here. A second one is WebArena. And WebArena was actually one that we created here, but in my lab at CMU, but a lot of people use it to evaluate web agents. And basically the way it works is you set up a bunch of different websites, and these are all open source versions of something you might think are popular websites. So there's One Stop Shop, which is an open source version of basically Amazon. It's a shopping site. You have a content management system. So this is the content management system for One Stop Shop. So basically you go in and add items to a store and other stuff like that. We also have an open source version of Reddit called PostMill, an open source version of GitHub called GitLab. So these are kind of production grade open source sites. And then we have a lot of other information sources like Wikipedia and stuff. And then the agent goes through and tries to answer questions like, tell me how much I spent on food purchases in March 2023, or create a Nolan fans repo listing Nolan's Oscar-winning films in a README file. And there are lots of tasks, complex multi-step web interactions. So this is kind of a standard web agent evaluation benchmark. Another area where people use agents, like I talked about before, is research. And so a kind of standard version of this is Gaia. And Gaia is basically a research benchmark where you need to find things like, or it's kind of a general assistance benchmark with like leaning towards research. And so it's like, what is the enrollment count of this clinical trial? You know, read this label and tell me about it. Read about NASA's astronomy picture of the day. And so a lot of, you know, the idea is that this allows you to do research. This was created by Hugging Face and Meta, and they actually just released about last week Gaia 2, which I haven't tried out yet, but it's supposed to be kind of a modernized version of this. So you could also check that out. There's a lot of other evaluation benchmarks that you can use, and I would maybe like to highlight a few of those. So in the Open Hands repo, we have an evaluation benchmarks directory, which has like 25 different benchmarks, which are all implemented. And these cover things like coding all the way to like general assistance to web navigation, other stuff like this. So this is one example. Also recently, a company called Prime Intellect released a environment hub, which has a bunch of environments. The environments could be used for training or evaluation, but I would say that most of these are more like evaluation environments. They're not like training environments. But this is another place that you could look to find lots of environments. The ones in the Open Hands Hub will skew towards being like practical ones that like immediately you could see the usability of. The ones in the Environments Hub for Prime Intellect will be more on the ones that are like more sandboxed and like simpler to run. So if you want to do like a research project, I think the ones on the Environments Hub might be a good place to start. And then when you want to graduate to things that are more complex or kind of real world usage, the ones on the Open Hands are probably better. And they kind of like overlap to some extent. There are some that are included in both. Cool. Any questions here? Another thing is this is very expensive to evaluate. So if you want to work on inference and make this faster for me, I would be very happy. The next thing is critic models, and I'd like to talk a little bit about this. So critic models for agents, the motivation here is it can help to have a second opinion about how well your agent is doing. And there's a couple use cases for this. The first use case is to re-rank multiple candidates to increase accuracy. Another is to audit to ensure safety. And so safety or maybe just like performance. And so to give an example of a paper on re-ranking, this is a paper that we did with people in collaboration with people at UC Berkeley. It's called SWEGEM. And basically, there were two parts to this paper. The first part of this paper was just training software engineering models through reinforcement learning, or software engineering agent models through reinforcement learning. But the second part was training a critic model to re-rank multiple candidate trajectories, agent trajectories. And the basic idea is that you want to perform inference where you roll out n times and then pick the best output. And basically what we showed is that if you started out with a model that had about 20% accuracy at the time, every time you double the number of rollouts you do, you see an approximately constant gain in the amount that the score increases on Sweetbench. And we were able to get from around 20 to up to 32 here. And so basically, if you really want the best benchmark score, this is super effective at getting the best benchmark score at the cost of having to run inference like 16 times, which is very expensive because running agents is expensive already. And if I haven't convinced you that this is something like important, we were just talking about Claude Sonnet 4.5 coming out. And if you look at their results here, the dark bar is single instance inference, and the light bar is where they did lots of rollouts and then they re-ranked them. And so this is what everybody does when they want to when Anthropic wants to beat OpenAI, and then OpenAI wants to beat Anthropic, or we want to beat whoever else. So in reality, I don't know if there's that many people who use this in like a production setting, but like let's say you were working on a agent to run like a machine learning experiment or something like this, and you really wanted it to succeed, and you could spend $10,000 on making sure that it succeeded, then this could be a viable option for something like that. And then the way it's trained, actually, sorry, I totally, this is the first time I made the slides, so I forgot a few slides, but basically the way it's trained is pretty simple. What you do is you do a rollout of the trajectory. You evaluate the rollout using the like unit tests that you have to evaluate the output. And then after you've evaluated the output, you train a model to predict whether the output was correct or not. So this is the simplest way to do this. When we talk about reward models, in the future classes, this is an outcome reward model. Another way you can do this is an outcome reward model predicts only the final outcome. So you basically predict the final outcome. Another way you can do this is come up with some sort of intermediate reward step by step and try to predict how successful each step is. This is called a process reward model, but coming up with the supervision for this is much more complex. And we'll probably talk about that in the reward models class. Cool. Any questions here? Yeah.
You can also, like, just to verify if the agent solved an issue or not,
Mhm.
we can also use tests.
Yeah.
Then, like, why do we want to, like, why don't we generally train models that can predict tests instead of training a models that can, like, predict from a trajectory, because that will be system agnostic?
Yeah, that's a great question. So we can tell success from whether unit tests pass or not. So why don't we just train a model that's really good at generating unit tests and then use the unit tests to decide whether it passed or not? I think we should do that. Honestly, I think that would be great. But unfortunately, models are not all that great at generating unit tests. And then, like, let's say some unit tests didn't pass, you might still be successful. There are some tasks that are not necessarily easily unit testable, like a research task or something like that. So like there are situations where this would not be an appropriate solution, but I think overall for software engineering, it is a very appropriate solution and we should work more on it. There's a benchmark that I didn't talk about called SWT bench, which is software testing bench that tests, and also test Gen-eval. There's other benchmarks like this. And I really wish that these benchmarks get more love. Like I think software testing sounds boring until you realize that if you can write a really good unit test, the agent can usually solve the problem for you. And so I think we can focus more on that sort of stuff. Cool. Any other? Okay, great. I'd like to talk a little bit about multi-agent systems. And so there's a number of reasons why you'd want to use multiple agents. The first reason, which at least until about 6 to 12 months ago was a very popular reason to use multiple agents is specialization. And the idea is you can have different agents solve different tasks. And there's usually an analogy, which is like, in a software company, you don't have one person who is planning and implementing and doing quality assurance and other stuff like that. So we should have different agents to do these things. I kind of agree that this is true in a software company, or I definitely agree that it's true in a software company. But on the other hand, we have an LLM that can do all of these things well, and LLMs kind of like absorb all of the specialized knowledge and can memorize like things that far beyond what humans can memorize. So I'm a little bit less convinced that this is a good motivation for doing multi-agent systems, especially now that we have language models that are pretty good at doing individual tasks. On the other hand, there is a really strong argument for doing multi-agent systems when you have complex tasks that can be easily parallelized, because you can have one agent do one part of the task, another agent do another part of the task, another agent do another part of the task. So I think this is a strong argument to use multiple agents. One comparison you can make if you subscribe to both ChatGPT and Claude is try to do a research task for on the OpenAI ChatGPT deep research, and then also do it on the Claude deep research. And the Claude deep research does this sort of task parallelization. It will have a kind of like master agent delegate a whole bunch of different research tasks to different agents. And then OpenAI will be doing everything in serial. And you'll see OpenAI will look up like 30 references and Claude will look up like 300 references or something like this. And you can see the results from Claude are much more comprehensive. So this is a good example. This is hard for software engineering tasks, for instance, because like very often it's hard to decompose the task together without having like conflicts between the code you write and other stuff like that. But it's still possible there, it's just harder. Another reason could be for robustness. And so, like, for example, you might delegate 4 different tasks to 4 different agents, and then have another agent like double check. So it's kind of like the agent is doing like the agent is acting as a critic model. So after one agent has finished the task, you go back and double check its work. So there are benefits there as well. And so why not use multiple agents? There's more components to manage and integrate. Task decomposition can be tricky. Another issue is communication difficulties. And what I mean by this is when you're implementing a system with multiple agents talking to each other, you want to make sure that exactly the correct context is passed. So you don't necessarily want to pass too much context, because there's kind of an advantage of an agent like solving a task and then kind of that task summary just being passed back to the main agent. But on the other hand, a very common failure case that we saw is like we used to have a web browsing agent within OpenHands that was separate. Now we just have one agent that does web browsing. And the web browsing agent would do a whole bunch of information gathering, and then it would give a very brief report back that wasn't like sufficient. And like the coding agent would be like missing information that the web browsing agent actually discovered during its process of web browsing. So you need a really good, effective way of passing context together. Yes.
Context pass always in form like tokens and not saves, like logits or even deeper representations.
Why is so good question. Why is the context not passed in the form of logits or deeper representations? I think that would be possible. I think probably the biggest reason why is because many of the best models for being agents are proprietary models, and you're not able to easily do that with proprietary models through an API. But I think if you could demonstrate that that was very useful with open models that you could use for something like that, then that could be valuable, and that might convince people who are building proprietary models to support that.
When feedback output into the the
Mhm.
next hidden state is always weaker than go to feeding the hidden state of one state to the next one. And that's because of this information loss that happens. So
Yeah, I agree. Good idea. So there's a bunch of frameworks. We talked a little bit about LangGraph. I'm going to talk a little bit about AutoGen. But basically there are frameworks for building multi-agent systems. And usually what they do is they kind of give you the scaffolding to do this sort of context passing, implementation of tools, and other stuff like this. So I think for quickly bootstrapping a system, especially an agentic system with a very fixed workflow, not something more complex like, research or like arbitrary research or coding, but something more like I want to process this file that a user has uploaded, extract this fixed set of information from it, and then upload it to a database. Then these sorts of fixed workflows are quite helpful. And so they give you things like customizable agents, flexible conversation patterns. They can also pass things to humans if you want.